All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying, let's determine the shear force and bending moment at point B in here. So to do this, we're going to try to set up a section where I slice straight through point B, and then I'm going to make a free body diagram that goes around through point A. If we can include the tip of a triangle when we do these, it will always be easier than trying to figure out a trapezoid and working with that. So let's do circling to the left. If I'm doing that, I need to figure out AX and AY. Let's come in and make a free body diagram of everything, the entire beam, apply equilibrium, and find my support reactions. So we'll start there. I'm going to draw my beam. At A, there's a pin, so I have an AY and an AX. And at C, I need to have a CY. Along the top, there is a triangular distributed load that goes to a maximum height of 200 pounds per foot. And my entire width of this is 3 feet. So we can come in here and start trying to work with that. Let's move that 2 over just so it doesn't hit the dash. 200 pounds per foot. If I'm trying to find my support reactions, let's just start by summing moments at A. With positive going counterclockwise, let's sum up my moments about point A. That would get me 3CY minus my moment from the distributed load, force times distance. The force is the area, so 1/2 3 times 200 times my distance. I want to measure from A. I'm going to go first to the 90-degree corner, so that'd be 3 feet in. But then I come back towards A third of the base, minus 3/3, or really that'd just be 2 feet. But that's it for us. This is force, this is distance, this equals 0. And I can solve for CY. I'm going to get it's 200 pounds going up. CY is 200 pounds going up. And I know it's up because this equation solves to give me a positive answer for CY, which means I guessed the right direction in my free body diagram. And with that known, let's sum forces in the Y. Summing forces in the Y. We have AY going up. We have CY going up, plus 200, minus our distributed load, or minus 1/2. Our base is 3. Our height is 200. It's going to get me to 0. Which if I solve for AY, my only unknown in here, I'm going to get a positive. AY is 100 pounds going straight up. Finally, I could find AX as well. If I sum forces in the X, all that I have is AX. It has to be 0. And that gets us through my support reactions. If we compare this to our last example video, which we'll try to link in here, I had something where AY was 100 pounds, CY was 200 pounds, it was 3 feet wide. Rather than a triangular distributed load, I had a 300-pound force, which is this area, 1/2, 3 times 200 is 300 pounds, and I located that right at point B. We're really trying to come in here and compare this externally identical, our support reactions are the exact same thing, object to one where I put a concentrated force on versus a distributed load on. See how that changes and everything. So let's come in and go for it. So we have our support reactions. We can start making our section free body diagram. So we're looking at just AB when we do this. So we can make our free body diagram. I go from A over to point B, where I make a cut in here. This is point B. It's 2 feet. I know AY was 100. When we dealt with just a single concentrated force, we said if we were making a cut just before point B, we wouldn't put on the concentrated force. Just after point B, we would put it on. For this, it doesn't matter. We can cut right at B because we have a distributed load. So we're going to reapply our distributed load. Our 0 point in this is at A. And we're going to call this maximum point here WO. I'm just giving it some variable name. It's not 200. It's 203 feet in. I made this cut 2 feet in. I can't say that's 200 or everything's going to come out very wrong for us. My first step is going to be, let's find WO. I can use proportional triangles for that. So in this triangle, our ratio of height to base, WO over 2, is equal to this triangle, height to base, 200 over 3. Or our WO is going to work out to be 133.33 pounds per foot. In my free body diagram, I need two other things. I need to get in here my shear, positive shear, and we'll always set this up assuming positive, causes a clockwise rotation about the opposite end from the cut. So our opposite end is here at A. Our positive shear, VB, will be going down to cause a positive shear, a clockwise rotation. Positive moment causes our top to go in compression. Again, if we think of kind of the hollow space in my hand as a beam, or my fingers are the beam, if I curl my arms up, I'm putting a moment onto the beam. My thumbs spread apart, my fingers squish together. The top is going in compression. I did that when I put a counterclockwise rotation on here. So a positive would compress the top of this. So this would be my MB. I need to find VB and MB. And we can just apply equilibrium for that. So let's start and just sum our forces in the y direction. I know my height of the triangle. I know my base. I would get, AY goes up 100. My distributed load comes down minus 1/2. My base is 2. My height is WO, 133.33. 1/2 base times height. Minus our shear, minus VB, equals 0. Or if I solve that for VB, I'm going to get that the shear at point B is negative 33.33 pounds. When we did just that single equivalent concentrated force, we went just before point B, we were at 100 pounds. Just after, we were at negative 200. That's significantly different than what we're getting here. We got to apply that distributed load in here. Don't work with the single equivalent concentrated force. It causes all kinds of problems for you. It's useful as we're setting things up to think through what are you doing. Really quickly, start drawing it as a distributed load again, or you're going to get very wrong answers coming out. And that's going to be true on the moments as well. For the moment piece, no matter what, we were at 200 pound-foot before. Let's see what we get here. If I do positive is counterclockwise, and I sum my moments up about point B, I'm going to get, I have my MB. My 100 would cause a clockwise rotation. So minus force is 100 times distance is 2. My distributed load will cause a counterclockwise rotation. So we'll add this in. Plus force is area, 1/2, 2 times 133.33 times distance. I want to go 1/3 of the way in from the 90-degree corner, which is at B. So just 1/3 of 2 would be 2/3. And then finally, that's everything causing moment. We can set this equal to 0. Which, if we solve for our moment, I'm going to get to that moment at point B is 111.11 pound-feet. Again, a very different answer than what we got when we used the single equivalent force. Even though externally our support reactions worked out to be the exact same, whether it's a distributed load or a concentrated force, makes a very, very critical difference for us when we look internally on that. Go back and work with the distributed load every single time. Don't try to do the concentrated force equivalency on these. It's going to cause more problems than it's worth. We should try to take that step and work with the actual distributed loads. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around. Let's get you an A with JJ.